We're starting the last day. If I put somewhat to time, I hope we have everyone hopefully here. No one has lost in the bus or something. So anyway, so this is our last day of the workshop, and we will start with Oleg Lisovyi talking about Painlevé, Painlevé 1.
Yeah, thank you very much. There are many people that I would like to thank here. So first of all, Alessandro and Giulio for keeping organizing this nice workshop. Then I would also thank Kianyu Hao, who kindly agreed to swap our talks. So I'm going to talk about this Painlevé 1 equation, which is a simple ordinary nonlinear differential equation, which happens to be related to three rather different stories. So the first story is about the two-dimensional conformal field theory, which as we will see, so this will be my main topic today. So this story relates the general solution of the Painlevé equation to irregular conformal blocks of the Virasoro algebra. So the second topic related to P1 is topological recursion. And well, it turns out that very similar formula that you have over here, basically this Fourier type formula that you have already seen in the talk by Harini. So you also have in the topological recursion story. And the third topic, which turns out to be related to this general solution of Painlevé 1, is the four-dimensional supersymmetric gauge theory. So historically, when this formula for Painlevé 6 in terms of Virasoro conformal block was written, well, of course, we tried to do something similar for all the other Painlevé equations, but we succeeded only in the case of Painlevé 5 and Painlevé 3. So these are easy limits which correspond to well, decreasing the number of flavors in the gauge theory from nf equal to 4 all the way down to nf equal to 0. But so the consideration of this of the Painlevé equation like P1, P2, P4 was out of reach. Well, essentially because we didn't know how to even define the corresponding irregular conformal blocks. So what we tried to do then with Giulio, Alessandro, Katsunobu, and Antonio Sciarappa is that so we gave up on CFT and we tried to compare so this asymptotic expansions of the Painlevé 1 tau functions with expansions of gauge theory partition function that you can compute using the method which is called holomorphic anomaly. And indeed, we have found a match here. Then there was this second advancement which related topological recursion. And finally, so the CFT story finally has received some insights very recently in this paper by Pogosyan, which I will try to actually, I wanted to say improve that, but actually I will give you some alternative to that. Okay. But let me refresh your memory on Painlevé 1 first. So it's this differential equation. So Q is a function of T, no parameters here, in contrast to Painlevé 2. So no special function solution at all. So sometimes it is convenient to introduce here this h bar parameter, but it can be killed by scaling. rescalings of the function and independent variable. However, so if you are interested in this topological recursion and holomorphic anomaly stuff, then actually you are expanding there in h bar. So it is, sometimes it is kind of important. Now, we define the tau function in this way. So this is basically some antiderivative of the standard Painlevé-1 transcendent. And so the Painlevé property of absence of complicated movable singularities means that any solution of this equation is meromorphic in the entire complex plane of T. And why the first hint on why the tau function is a better object is that, well, the tau function happens to be holomorphic. Now, second important fact about this equation is that it comes from isonodromic deformations of a certain rank 2 linear system on the Riemann sphere. So the system is here. So what is important to notice here is that so you have a third order pole at infinity, which corresponds to this x square here. But the fact that the coefficient of x square, as you see, so this is non-diagonalizable matrix. So this means that we have a ramified irregular singular point of Poincare rank 5/2. So for example, if you had also x squared somewhere here, then that would be an irregular singular point of Poincare rank 3. Okay. Now, so we have this spectral curve, which in this case happens to be just the Weierstrass elliptic curve. So this is the input that you need to run both the topological recursion and the holomorphic anomaly. And so H here is the Painlevé-1 Hamiltonian. So Painlevé-1, of course, can be written as a non-autonomous Hamiltonian system. Okay, now the theorem that I have explained 1 year ago here is that so the general solution of Painlevé-1 for the tau function can be written in the following form. So this is a Fourier transform of, or better to say, Zach transform of some more elementary function, which is called T here. And so the parameters nu and rho, they correspond to two integration constants of our differential equation. So this is why I'm talking about general solution. So the function tau here is a genuine function. It's not something like an asymptotic series. It is defined by the tau function itself, which is a genuine holomorphic function. And so this nu and rho, they are actually very simply related up to some factors of I and so on. They are simply related to Stokes coefficients of this auxiliary linear problem that I have shown. And so basically, the analog of this statement, if I am talking about Painlevé 1 transcendent itself, so this function q of t, so the analog of this statement is just trivial. Basically, it tells you that q is uniquely determined by nu and rho, and so q is a periodic function of both rho and nu. But the tau function is not. For the tau function, you have this quasi-periodicity. You can have periodicity with respect to only one parameter. So here it is rho. And with respect to the other one, so if you put here, if you replace here nu by nu plus 1, you will earn some extra numerical factor. Okay. Good. And now, so what we have done back in 2016 was just, so we have asymptotic results on Painlevé functions obtained in the late 80s, early 90s by people like Kapayev, which give you the leading asymptotic behavior of this function tau. And it is not difficult just to plug this back into the differential equation and compute more terms in the asymptotic expansion. And it turns out that, well, this asymptotic expansion organizes into this structure. So it's not very important to remember all pieces of this formula. So one thing which is probably worth noticing is this Barnes G function, which appears here in the structure constants. So this satisfies a certain recursion relation, and in particular, this function vanishes on negative integers. Okay, and similar asymptotic expansion holds. I mean, for the tau function itself, similar asymptotic expansion holds along any of these 5 rays in the complex T plane. So this is related to discrete Z5 symmetry of Painlevé 1. Right. And so the most important object that I will be interested in today is this series, well, in inverse powers of isomonodromic time, basically, so this combination S. So it's this calligraphic Z. So the coefficients of this Z, they are polynomials of degree 3k in mu, and well, they are even or odd. Now here comes the first surprise about this series. So if instead of, let's call this partition function, if instead of partition function you consider now the free energy, so if you take the log and re-expand, it turns out that so this free energies Ek, they are polynomials of degree only k plus 2 instead of what you would naively expect. And for those of you who kind of already know what I'm going to talk about, so this is of course related to the existence of quasi-classical or Nekrasov-Shatashvili limit. Yeah. Mm-hmm. Mm-hmm. Yes, basically somehow the symmetry of P1 is inherited from this symmetry of the linear system. But in order to make this statement, it's not even necessary to know anything about the linear system. You just, look at the equation, try to rescale Q and T by some fifth roots of unity, and you just see. But yeah, so I would rather say that this Z5 in the complex Z plane of the linear system comes from Z5 of P1. Right, and there is one important special case here. So, for example, if you set this parameter nu equal to 0, then because of this vanishing property of the Barnes G function, so in this sum, all terms with negative n will disappear. And then we can further send this parameter rho to I infinity, so that the terms with positive n also disappear. So then we are left in here with just one contribution coming from n equal to 0. It is this, so I write it in this form. And so this gives you like the most famous asymptotic solution of Painlevé 1, which corresponds to the so-called Tronqué solution. So actually, you have no parameter here, But in fact, this expansion describes a one-parameter family of solutions which differ by exponentially small corrections. Yeah, and anyhow, so our goal is to relate this asymptotic series like Z to Virasoro algebra. So now let me start with a toy example, which is aimed at those who have never heard about these things. Probably there are very few people like that in the audience, but it will be, yeah? Yeah.
Is there like this phenomenon that if you tune a parameter, then you get only a sum over non-negative integers? Is it observed also in other?
Yes. Yeah. It's.
Do you know it of this kind as well?
Yeah, all kind of special solutions that you know, either like the special function solutions, Riccati solutions, or Fredholm determinant solutions. Usually, you don't have all of the terms in this Fourier sum. So in Fredholm determinants, indeed, you have like only a half, and in these things coming from Toeplitz or Hankel determinants, you can have just one term, or you can have n of them. Okay, so even though this example will be kind of trivial, but it will also allow me to set the stage and introduce the notation that will be useful in the following. So I'll start here from the SL2 algebra. So I take highest weight state, which is diagonalized by L0 and killed by L1. So then I build this highest weight representation, and I am going to look for a Whittaker vector living in this infinite dimensional space, which satisfies the following three conditions. So the most important condition is the first one. So it tells you that this psi has to be an eigenstate of L1. The second condition is a kind of normalization. Because you see, if I take psi and I multiply this psi by an arbitrary function of epsilon, so it's still an eigenstate. Okay, so this is a kind of normalization, but this normalization still contains an ambiguity, because now if I multiply this guy by a series in a form, it's a formal series in the parameter epsilon with coefficients in this highest weight module. So if I take this and I multiply it by a formal series starting just from the identity, I still get a series of the same form. So I still have some freedom, some ambiguity in this choice of psi. And I want to fix this ambiguity by requiring that in this GK, so in higher order contributions to the Whittaker state, there is no highest weight state, J. So there is a way to express this condition in this form. So if I use the standard bilinear pairing on this for this representation, but actually I would like to kind of avoid using the bilinear pairing as much as possible. So it's better to like state this condition in this form. And I will refer to this condition as the orthogonal gauge. Okay. So once again, so it tells you that when you write this vector in this basis over here, you don't want the highest weight state to be there. Okay. Now, if you plug now this series for Whittaker vector into the eigenvalue condition, so this gives you a certain recurrence relation on this GK. So these GKs are sums of monomials in L-1. And then, it is fairly easy to show by induction using also this orthogonal gauge condition that these GKs are given by this. So basically, there is only one basis element that contributes to GK. And then, so once we have this, we can define the conformal block of the SL2 algebra as the norm of this state psi. So we compute this norm. So here we just use the SL2 commutation relations, and so we end up here with an explicit series, which happens to be just the series for Bessel function. Okay, so Bessel function is the conformal SL2 conformal block. Now let us complicate this example a little bit. So this was the first paper of Gayotto, which has initiated this whole story about irregular conformal blocks. So basically, the only thing we change is that we replace the SL2 algebra by Virasoro. This means that our module now has this form. So we have here vectors which are labeled by partitions. So basically, if I want to explain what is something like this, so what is the L operator associated to this Young diagram, so we are going to have L minus 1, L minus 2, L minus 2, and I think so the notation is clear. Right, and so then we have this module, and we try to find a Whittaker vector satisfying the conditions analogous to what we had before. So this Whittaker vector has to be an eigenstate of L1. It has to be killed by all other positive Virasoro generators. And there is no change here. So this normalization and fixing the ambiguity. So now the eigenvalue condition and normalization, they give you these two recurrence relations. There are only two of them because so when you have L1 and L2 equation, L1 and L2 generate the whole of Virasoro. So you don't need L3, L4, and so on. These are satisfied automatically. And then, you just look for this sum of Virasoro monomials in some form. You have to introduce some ansatz here. And it turns out that in GK, you have these monomials with the total number of boxes in your Young diagram equal to K. Okay, this is also very standard, and this is you can compute in a very straightforward way. So I think that usually people do this using the Katz-Shapovalov form, but again, I want to avoid using the pairing as much as possible. Yeah, and then the Virasoro conformal block, which again will be given by the norm of this Whittaker state, is now given by this series in epsilon, which you can compute order by order, and well, there is thanks to the AGT correspondence, even explicit formula for the series, and so the statement is that this Virasoro irregular Virasoro conformal block satisfies the most degenerate version of Painlevé 3, so the so-called Painlevé 3D8 equation. So if you set in here the central charge equal to 1, and if you parameterize the conformal dimension, so this will correspond to this parameter nu, so the monodromy parameter of the associated linear problem. Okay, so now in order to treat more complicated Painlevé equations like P1, so we need more irregular vectors of the Virasoro algebra. And how to define this more irregular Whittaker states? So the general idea is to look for vectors which will be joint eigenstates of a suitably chosen subalgebra of Virasoro. So one example is this example here. So you take the subalgebra generated by L1 and LR, say, and so then commuting L1 and LR, you can get all of the other Virasoro generators, LR plus 1, R plus 2, and so on. And but on the other hand, since these generators act by just, so they give some eigenvalues, so all of the higher generators will act by zeros. Okay, so you want to take this vector. Another choice, which became with the time very popular, is to take the subalgebra which is generated by LR up to L2R. And again, so you define Whittaker state as the joint eigenstate of these operators. And then for all n greater than 2R, so the action of Ln should give 0. Okay. Sorry, can you repeat?
Here you just need two generators, which is L1 and LR. You don't need anything else.
Yeah, here it's just L1 and LR. Here you have R plus 1 generators.
What is the action of the generator in between?
Nothing, we don't know. Yeah, and but the real question is what to do next. So actually we have multiple problems. So the first problem is that, so suppose you want to introduce some algebraic definition of some conformal block, which would be related to your favorite Painlevé equation. It is not clear what algebraic construction you should use. So for example, even for Painlevé 5, where there is this limit from nf equal to 4 to nf equal to 3, so you have two different asymptotic expansion for large isomonotromic time, and an algebraic definition of appropriate conformal block is so far available for only one of them. So we just don't know what kind of expression to compute to be able to match it with this Painlevé 5 asymptotic expansion. So this is one problem. Okay. Another problem is that so here when I will try to so suppose we forget about Painlevé equations, take such a vector or such a vector, and try to build out of this vector some kind of conformal block. So we need to consider some pairings, okay, some scalar products. And when this R here is greater than 1, then you immediately run into problems, because look at this expression here. So you know, so this I2, if you look at this formula, so you have, so this I2 is an eigenvector of L2, L3, and L4, but you don't know how L1 acts on this guy. And on the other hand, you don't know how this L1 acts on the dual highest weight. Okay, so all of these scalar products, there is no canonical way to compute them. In contrast to the case where you have here rank 1. Okay, yeah, and by the way, now I can explain some conventions. So you see the fact that here the eigenvalues are non-zero up to 2R. So in this case, we are talking about Whittaker state of rank R. Okay, and if you go back to this to this example here, for example. So you see here we have all just one eigenvalue at 1. So this is why I'm talking here about rank 1/2. Okay. Right. So there is, because of the absence of a canonical pairing, there is a huge ambiguity here. Basically, you can just introduce in this way an infinite number of parameters in the corresponding conformal blocks. Okay. Okay, and there is a way, conjectural way to fix this ambiguity, which was suggested by Gayotta and Teschner. Okay, so let me first recall some kind of well-known things. So if you start from the Heisenberg algebra with this generators and relations, so there is this Feigen-Fuchs bosonization of Virasoro, which expresses the generators as well, at most quadratic combinations of this AK. Okay. And so the Q which appears here is related to the Virasoro central charge in the standard way. And now using this embedding, we can construct a certain anti-homomorphism of the positive part of the Virasoro algebra into an algebra of differential operators in this parameters Cn. Okay, so these are just some complex numbers which you can fix as you like. And now, if you see it, if you look at what it gives you after the after expressing the corresponding Virasoro generators, so you see that exactly those generators with n between r and 2r, so they are given by just some numbers. So this ck essentially parameterize the corresponding eigenvalues of your Whittaker state. But now what you have in addition, so you have an action of the Virasoro generators from L0 up to Lr minus 1. Okay.
Can you say it again? So how many C's do you have?
Okay, I have R plus 1 C's, but not all of them are equal. So C1, so from C1 to CR, the C's from C1 to CR, they play the role, they are important, so they are parameterizing the eigenvalues, and C0 is kind of less important. Well, it is important, but it will characterize the embedding later.
Okay, no, my question was how do you have finite many or infinite many?
No, here I have finitely many.
In the formula in the middle, you just have m greater than 0.
Yeah, but now I say the following. So now let us let us now restrict our attention to the positive part of the Virasoro algebra, first of all. And so in that case, so you are going to have some formula for these LNs, and in those formulas you basically set all of Cn's with n greater than r equal to 0, and this is what it gives. Yeah. So this, so if you like, we are using this Feigen-Fuchs bosonization just to guess this differential operator realization here. Okay.
No, okay. So you said C is equal to 0. I mean, then you have difficulty that you cannot longer differentiate with respect to them.
Mm-hmm.
So, but maybe you don't have such terms as L plus. I mean, you mean so this Heisenberg algebra, then from Heisenberg algebra to the algebra differential operators.
Yeah.
But there is no homomorphism from the algebra differential operators somewhere that sets C equal to 0, because C do not commute with differentiation. So this is an illegal operation. But maybe if you don't have differentiation, then some subalgebra is legal.
Maybe we can discuss this later, but you can just, if you don't like, you can just, I mean, forget all of this and just consider this differential operator realization and check the Virasoro commutation relation. So very pedestrian approach, but yeah. Okay, and so now what was the suggestion of Gayotte and Teschner? So the idea is that you do, well, you are trying to do something similar to what we had before. So you introduce, sorry, I don't have here the, okay, so I introduced the irregular state or Whittaker state of rank R of Virasoro algebra in this way. So these L's with positive indices act by some differential operators that I have shown you before. So a part of them are just eigenvalues, and those from L0 to up to L R minus 1 are some first order differential operators in the eigenvalues. Okay. So this is the starting point, and then so we look for a solution of this equation in the form of the following decomposition. So we are trying to embed rank R Whittaker state into a rank R minus 1 Whittaker module. And so we look for this embedding. So recall that with SL2 and Virasoro before I was looking for the Whittaker state in the form of a series in epsilon in the eigenvalue. So here it is a series in the like highest eigenvalue, so to say, the eigenvalue of L to R. And so this generalized descendants that you have over here, so this is like the Whittaker state of rank R minus 1. Here you have generalized descendants where you have similarly this Virasoro generators, so monomials parameterized by partitions, but you also have derivatives in all of the C's. Okay. And you have some prefactor here, which is a function of all this parameter C, which is unknown at the beginning. And now the proposal is that these equations fix both the form of this prefactor that you have here and the form of the generalized descendants. Okay, and this was checked by examples going to some sufficiently high order for some rank R equal to 2, rank R equal to 3. But as far as I know, there is no proof of this statement. And a typical answer for this prefactor is this. So you have some power of this highest eigenvalue and the exponential. Okay. And so basically what you are doing here is a kind of inductive procedure. So you embed IR into a Whittaker module of rank R minus 1. And so the Whittaker state R minus 1 is embedded into a Whittaker module R minus 2. And so at every step of this recursive inductive procedure, so only a finite number of parameters appear, of new parameters appear in the expansions. Yeah.
gauge coupling constant in physics, and all the others are like other parameters in physics?
I guess, I don't know about other parameters, but CR, right. So the CR are basically isomonodromic times, if you want. Right. And okay, so now what is our problem with P1? I have already mentioned one, that first of all, it is not very clear what should already be the algebraic construction. But there is an additional problem in the Painlevé 1 case, because there you know that you would need Whittaker states of half integer ranks. And so there was this proposal by Pogosyan and Pogosyan, which mimics in a way Gayota-Teschner, where, well, you try to play the same game. So now, talking about Whittaker state of rank 5 half, this means that I need, so I want to have L3, L4, and L5, which act by numbers. Then the other one should give you 0. And here you just plug an answer. So you want this else act by first order differential operators, which would respect the Virasoro commutation relation. And this is, well, the answer which you can just compute.
So I think that this lambda is more or less the same as C before?
Yes. So C was just a parameterization of this lambda. And actually, like Pogosyan and Pogosyan, they did this construction only for rank 5 half. But one can actually write explicit formulas for any half integer ranks. And all you need to do is basically, so in these formulas of Bosonization that you use to guess the answer here, so you just have to consider half integer indices of C's and set Q equal to 0, for example, because you only care about the positive part of the Virasoro algebra which doesn't know about central chatting. Okay, and then so for any half integer rank, you can write an explicit formulas of this type. So this.
Probably because there are no half integer generated. Wasn't becomes half integer. You just don't have a half integer Virasoro mode. So there is no term delta R0 because R is half integer.
But this is the answer to which question?
No, it just says that it is about positive part Virasoro, and then that it's about half integer versus half.
I do not even care about bosons. Sorry, I just want this this kind of formulas. And what I'm saying is that there is a way to guess them from bosonization, and then you easily prove that this differential operator realization is actually unique up to gauge transformation. I think in their case it was just computation. No, you fix eigenvalues. Then here L2, L1, L0. Yeah. So you just put the derivatives with respect to lambda 4 and lambda 3, and then you basically what you are trying to adjust is the coefficients here.
Yeah, also the coefficient, so the second term of the first line, so lambda 4 squared minus 4. Has to be computed.
Yeah, you can ask the computer. Yeah, but here again, so this is precisely parallel to Gayota-Teschner. So the generalized descendants have this form. And now the advantage is now you can compute, indeed, define and compute conformal block, because, well, this ambiguity that I had before with, say, L1 generator does not appear. So suppose that we have some L1 generator in between these two. Well, we know that L1 kills the vacuum. Okay. Okay. But now I should say that this approach, so indeed it allows you to define conformal block, but it leads to extremely complicated answers. One of the reasons why the answers are complicated is because we have not taken into account here the global conformal symmetry. So, for example, if you take a Whittaker state and you act on it by something like exponential of L0 or exponential of L1, so this will give a new Whittaker state, but with eigenvalues which are rescaled in some way. Moreover, so you see, if you compute this conformal block, so this will be a function of lambda 3, lambda 4, lambda 5, but like anticipating the result that this will be related to Painlevé 1. So in Painlevé 1, you have just one variable, one isomonodromic time. So in fact, this function here will non-trivially depend only on a certain irregular cross ratio, so to say, which will be a certain combination of lambda 3, lambda 4, and lambda 5. Okay, and so this is somehow this is not taken into account into these formulas. And what we are going to do, in some sense, is precisely that. So we are sort of trying to, from the very beginning, to work in the with appropriate isomonodromic time and to eliminate all extra parameters. Okay, so now what is the construction? So we start from a rank 2 Whittaker state. So rank 2 means, once again, so you have some eigenvalues from L2 to L4. So the eigenvalues I choose in this way. So this will be 1/4, 0, and minus nu, some parameter. So the fact that I'm choosing them in this way is not a loss of generality, because once again, I can act on this by a like Virasoro group-like element or SL2 group-like element, and so this will change the eigenvalues, and so I have fixed two of them as I like, and I like 1/4 here and 0 here. Then, so once I have this, and I know nothing about the action of L1 and L0. Okay. Now I consider, let us consider the module induced from this Whittaker state. And we are now going to look for a Whittaker vector inside this module, which satisfies the same three conditions that I had before. So this is the eigenvalue condition, and this is the normalization and fixing the ambiguity. So in the eigenvalue condition, so you have to notice the following. So there is this epsilon here, and if we have epsilon, so this will eventually become isomonodromic time. So if we set epsilon equal to 0, then so this disappears, and so these eigenvalues are the same as we had here for rank 2 state. So this is why I'm going to look for psi in the form of the series. So for epsilon equal to 0, we have just this rank 2 state.
Just compare. So in the equation 1, as is the same in Poisson case, but now you give complete matters.
Well, I do not have L0, L1, and L2 of Pogosyan here at all.
They had 3 eigenvalues.
Yeah, so the 3 eigenvalues, they were like here in lambda 5, lambda 4, lambda 3.
And yeah, you said the 3 eigenvalues equal to some 0, 4, and that. So
yeah.
You said that everything depends on the cross ratio, so you use this secretly.
Yeah.
You understand that you use this
Yeah, but I start already from rank 2, so I use this symmetry already to fix something convenient here, and so this rank 5 half state, I want to it to differ from this guy by something small. Okay, I want by basically this this extra eigenvalue that I have in the rank 5-2 case.
You start from another construction representation.
Hmm?
You have another high square.
Mm-hmm. And so here I'm trying to avoid the differential operators completely. Okay, and so the main theorem is this. So the rank 5-2 5 half Whittaker state, which I defined, uniquely exists, and so this is the structure which I'm will try to explain now. So so what you have to do here is that you have to assign to each Virasoro generator in this monomial a degree. So the degrees of generators with negative indices will be the same as usual. So L minus K, so the degree is K, but L naught will have degree 2, and L1 will have degree 1. Okay. Now, what we are saying here is that so the Virasoro monomials appearing in the decomposition of this rank 5 half Whittaker state, so they will have the total degree at most k, and actually equal to k modulo 2. Yeah, that's it. Okay, and it turns out that this linear combination is optimal in the sense that, like in practice, you see in computation that all of the coefficients in this decomposition, they happen to be non-zero. Unlike like if you know these papers by Pagassian, we have many complicated coefficients. Some of them are equal to 0. You don't know which a priori. You just have to compute. You don't know either what is the like the general ansatz, what is the optimal ansatz that you have to feed to Mathematica to compute the state. So here I tell you the algebraic answer. So, for example, if I want to compute this G1, so what kind of terms, what kind of Virasoro monomials can I have in G1? So first of all, L minus 1, which is of degree 1, but also L1. Okay. If I want G2, I'm going to have L minus 1 squared, L1 squared, L minus 1, L1, but also L naught. Okay, so 5 different monomials, and so on. So I have absolutely no time to say anything about the proof. So both parts, the existence and uniqueness, they require some hard work. But once you have proved, these guys can be very easily computed. So here I give you some expressions. So this is G1, this is G2. So this is G3, so the third order contribution to the Whittaker state, which took, I think, more than one page in the paper by Pagassians. So this guy here. And this guy, they told that they computed it, but it cannot be usefully inserted into the paper. And here it is, I mean, it is okay. And in fact, if you are now interested in conformal blocks, okay, I have not yet defined conformal blocks, but let me say that. So if you take this G4, so this guy is responsible to the for the very first non-trivial contribution to the expansion of the tau function. It is responsible of this term here. And G2 is responsible basically of this minus 1 over 60 minus nu squared over 2. Okay. But with this differential operators, I think you simply cannot go beyond G4. Whereas with algebra, so we have stopped at level 12, if I remember correctly. But in principle, one can do much more. Yes. I'm going to make an exact statement just very quickly, since I have almost no time left, about conformal blocks. So you see, so far we didn't need differential operators, but for conformal blocks we do. So for conformal blocks, so we need basically the action of L2 in a way. And so what we do here is that we introduce a certain linear combination of L0, L1, and L2. We consider the Virasoro subalgebra generated by this guy and all else with n greater or equal to 3. And so we require that so these guys act by the eigenvalues that we had before, and this guy acts as a certain differential operator in epsilon. And the form, so why this particular combination? Well, this is the only combination which will not change these eigenvalues here. Okay, so so it's not a guess. This is something which is like directly computable from the commutation relations. And then we do things a la Guyot and Teschner, but we only have one differential operator in epsilon. We define conformal block in this way. And so the equation which determines conformal block is this equation here. Okay. So the conjecture here is, sorry, I forgot to say. So as you see, so the irregular state that I have introduced by this equation, it should be proportional to the Whittaker state I had before. So the eigen value conditions are exactly the same. So it can only differ from this psi by a scalar factor, which will be conformal block itself, computed in this way. Okay, and so then while we cannot prove yet the existence of solution of this equation, the uniqueness is very easy. So you just have to, so here I just write the corresponding action of else by differential operators, and if we project this equation on the vacuum, then we obtain the conformal block in this algebraic form. So the expansion coefficients of conformal block, they are fixed by this type of Virasoro commutation relation. So this is like very easy computation. Right, and you can actually consider this as the definition of irregular conformal block. You can compute its expansion and match with the expansion of Painlevé tau function. And so the final conjecture, which is a reformulation of this result by Pogosyan and Pogosyan, is that, well, for C equal to 1, this like algebraic definition of irregular conformal block of rank 5½ reproduces this Painlevé 1 tau function building block Z, like here. And the identification is this. So epsilon is indeed basically S. Okay, that's it. Thank you very much.
We have still time for a few questions.
So, maybe this is a more general question. I mean, it's not only for this case. So, in the case of regular singularities, we can study study a degenerate insertion, and then we study its monodromies using fusion and braiding. What is there an analog like for these states? Like, is it possible to study to see the Stokes phenomenon?
So
To study a solution of the linear.
no, it is definitely possible to study, and there was a recent paper by the same authors, Pagasyans, where they study basically. So again, with this differential operator approach, but they study this irregular conformal block where you add a degenerate insertion. So you have BPZ. Yeah. So,
what's the analog of like fusion and braiding?
this is a. So you can do it for when you fuse degenerate field with this irregular state. You can kind of guess. But in general, if you ask me how to fuse like this I5 half with another sufficiently complicated state, irregular state, I don't know. So this is actually the main question if you want to have this construction for all the other remaining Painlevé equations. Yeah. So the question is about how do you do this irregular fusion.
Do you have a proof of the fact that the coefficients of conformal blocks are of order 3n
Like the first answer is no, I don't. But I think that well, no, I'm not sure it is. So you see, so what you easily compute from this commutation relations in this case is not the conformal block itself, but its logarithm. So it is probably possible to prove, knowing how these Virasoro generators act, it is probably possible to prove that indeed these UK are of degree k plus 2. So, but we didn't even try this.
then that fact follows from this simply by.
Yes. Then you just expand the exponential.
Is it clear that the same should happen for all such irregular conformal blocks?
What?
And this property also holds for Painlevé 4, I think, Painlevé 5, for all this expansion that have just one function in the numerator.
But which property?
That coefficients of conformal block have order 3n in
Yeah, I guess if you have a proof here, maybe you can extend it to that case. Because I didn't speak today about P2, where you can have similar formulas for both expansions at infinity. But for Painlevé 4, there are some extra decorations that you have to introduce. So I'm not. Maybe there are some extra complications. But okay, maybe I can ask later, why do you want this?
Any other last questions? If not, let's thank Oleg again.
Thank you.